Hello everyone, in today's lecture we are going to take limits of exponential functions. When we take log, then we can also call it as limits of logarithmic function. There are mainly three formulas and remaining formulas are applications of original three formulas. So let us take the formulas one by one. Number one, we are going to take limits as x tends to 0, a raised to x minus 1 upon x is equal to log a. Log a to the base e. In calculus, we always have natural log. Natural log means log to the base e. Now, if we replace this a by e, we get limits as x tends to 0, e raised to x minus 1 upon x is equal to log e, and log e is 1. And the third one is limits as x tends to 0, 1 plus x bracket raised to 1 upon x is equal to e. So these are the three main formulas. Now remaining formulas are the applications of this. For example, if you take log on both sides for this formula number 3, LHS will have a log of 1 plus x bracket raised to 1 by x as limits x tends to 0, and it will be equal to log e, and log e can be written directly as 1. Now using laws of logarithm, this 1 by x can be shifted as a multiplier of log, and therefore new formula we can write down limits as x tends to 0, log of 1 plus x whole upon x is equal to 1. In short, formula number 4 and 5 are one and same. Now in our earlier video, we already understood the concept of limits as x tends to 0, sin x upon x is equal to 1. And even if you write down sin mx upon mx, even though answer is 1, so same concept is applicable in formula number 1. So if you replace x by mx in index as well as in denominator, so again we get answer as log a to the base e. Why it is so? In this particular formula we can see that this index and this denominator both are equal to x and they are tending to 0. In similar case, if you take mx here in the index as well as in the denominator, so as x tends to 0, mx is also tending to 0, and that's why this formula can be applied directly. Similarly, in formula number 2, if you replace this x by mx, again we get same kind of answer whatever we got in formula number 2. And then in last formula, 1 plus px as x tends to 0 bracket raised to 1 upon x is also equal to e. Again same concept. If you see this formula number 4, this term is having tending to 0 along with the denominator of the index. So as x tends to 0, px is also tending to 0, and therefore if there is a constant along with x, the same constant must be there in the denominator of the index, so that we get answer is equal to e. So these are the basic formulas that we are going to use in today's lecture for limits of exponential functions, or also we can say limits of logarithmic functions. And then in latter part of this video we are also going to understand the concept of L'Hospital's rule. Let us take example number 1. Limits as x tends to 0, a raised to x plus b raised to x plus c raised to x minus 3 whole upon sin x. So here we are going to use the formula limits as x tends to 0, a raised to x minus 1 upon x is equal to log of a. If you replace a by b, it will be log b, or if you replace it by c, then it is log c. Now which are the adjustment that you supposed to follow, that we will understand one by one. First of all, we require x in the denominator to apply the standard formula, and that's why we have to create that x. So we can multiply by x and divide by x in this manner, and for sake of convenience I would like to split the term into two parts. So here we can write down limits as x tends to 0, x upon sin x. So that sin x is written first separately and we have multiplied by x. And then limits as x tends to 0, a raised to x plus b raised to x plus c raised to x, and then this minus 3 can be written as minus 1 minus 1 minus 1, and we can take whole upon x. So we can observe that here what adjustment we made? 3 is splitted and second one multiplied by x and divided by x. As we discussed in our earlier video that limits as x tends to 0, sin x upon x is equal to 1 and therefore x upon sin x is also equal to 1. You can take the limits of this particular part in this step. Doesn't matter if you take the limits and if you write down the value as 1. Since the answer is finite, you can take the limits of a particular term which is in the form of a multiplication or division of that particular term, multiplied by limits as x tends to 0. Now what we are going to do, since our standard formula is a raised to x minus 1 upon x is equal to log a, we are going to write down this term as a raised to x minus 1 plus b raised to x minus 1 plus c raised to x minus 1. And now we are going to split this x into 3 parts in this manner. So original value doesn't change. And now we are going to use algebra of limits. Since there is an addition of 3 terms, we are going to split the limits into 3 parts. So limits as x tends to 0, a raised to x minus 1 upon x plus limits as x tends to 0, b raised to x minus 1 upon x plus limits as x tends to 0, c raised to x minus 1 upon x. And now we are in a position to get final answer as log a plus log b plus log c. So standard formula we are using, limits as x tends to 0, a raised to x minus 1 upon x is equal to log a. And now we can use laws of logarithm further to get final answer as log of abc. So in this way we have solved this example. Example number 2 now, limits as x tends to 0, 9 raised to x minus 5 raised to x upon 4 raised to x minus 1. Again we are going to apply the same concept as that of example number 1. So first adjustment that we are going to do here, that is we need 1 for the formula a raised to x minus 1 upon x. So we need first minus 1 along with this exponential term. So here what we are going to do, we are going to subtract 1 and we are going to add 1. Time being, denominator we are going to write down as it is. Now here 9 raised to x minus 1 can be combined and also we can combine minus 5 raised to x plus 1. So we can write down limits as x tends to 0, 9 raised to x minus 1 minus into bracket 5 raised to x minus 1 whole upon 4 raised to x minus 1. So in this way everywhere a raised to x minus 1 this term is created. And now we are going to divide x to every term so that we will be in a position to apply the standard formula. So dividing by x to numerator as well as denominator, and when you divide x in numerator we can split this x in 2 parts straight away. So final answer we will get in next 2 steps. So 9 raised to x minus 1 upon x minus 5 raised to x minus 1 upon x whole upon 4 raised to x minus 1 upon x. So the adjustment is dividing by x to numerator as well as denominator. And now we are going to separate the limits everywhere. So we can write down limits as x tends to 0, 9 raised to x minus 1 upon x minus limits as x tends to 0, 5 raised to x minus 1 upon x upon limits as x tends to 0, 4 raised to x minus 1 upon x. So using algebra of limits, all these terms can be separated in this manner. And now we will use formula a raised to x minus 1 upon x is equal to log a. Here instead of a it is 9, so it is log 9 minus log of 5 upon log of 4. So this is the limiting value that we are getting. Using laws of logarithm, numerator can be combined. So it is in the form of log a minus log b, which is log of a upon b. So ultimately final answer that we get log of 9 upon 5 upon log 4. Example number 3 now. Limits as x tends to 0, 1 plus 5x upon 6 bracket raised to 1 upon x. So we can see that this is in the form of 1 plus px bracket raised to 1 upon px. We already learned this concept. If coefficient of x is 1 upon x we want, but if it is in the form of px, we should have same px in the denominator of the index. So we need to do certain adjustment in the indices. So limits as x tends to 0, 1 plus 5x upon 6 bracket raised to 1 upon x as it is. Now it is 5x upon 6. So we need here same term, same coefficient in the denominator of the index. In other words, what we are going to do now, we have to do the adjustment in the indices. So let us multiply and divide by 5 in the denominator. So 5 must be taken in the indices, whole bracket raised to 5 now. As well, we want 6 here. So 6 is to be multiplied and divided. Now we can see that 5x upon 6 is there and 6 upon 5x, that is a reciprocal which is placed in the index. So this adjustment you have to do to write down standard formula directly. Now it is in the form of limits as x tends to 0, that is 1 plus px whole bracket raised to 1 upon px is equal to e, and therefore we get final answer for this term as e raised to 5 upon 6. So we are getting the answer very quickly in minimum number of steps using this formula of 1 plus px whole bracket raised to 1 upon px. Now let us proceed for example number 4. So it is in the form of 3 plus x upon 3 minus x whole bracket raised to 1 upon x. So we need to do the adjustment again exactly in the same manner. So that is equal to, as far as standard formula is concerned, which is already written here, it is in the form of 1 plus px, means we need 1 there, and therefore we are going to divide every term by 3 inside the bracket. So limits as x tends to 0, so it will be 1 plus x upon 3 upon 1 minus x upon 3 whole bracket raised to 1 upon x. Now next adjustment, if it is x upon 3, it means that value of p is 1 by 3, and therefore we are going to do the separate adjustment for numerator and denominator, and for that I would like to separate the terms in this manner. So 1 plus x upon 3 bracket raised to 1 upon x upon 1 minus x upon 3 bracket raised to 1 upon x. Now in next step we will adjust that p value, means 1 by 3 value in the index in this manner. As well, it is better to separate numerator and denominator. So 1 plus x upon 3 bracket raised to 3 upon x. It means that we have multiplied by 3, so we have to divide by 3 in the index. And then denominator we are going to take separately. Limits as x tends to 0, 1 minus x upon 3 bracket raised to minus 3 upon x. In short, we have to do the adjustment with minus 3 now. So multiply by minus 3 and divide by minus 3 in the indices. Both are now in the standard form. So here value of this term is e raised to 1 by 3 and value of denominator is e raised to minus 1 by 3. We can shift e raised to minus 1 by 3 to numerator so that it will be e raised to 1 by 3 into e raised to 1 by 3, so that we can write down final answer as e raised to 2 by 3. Let us take new topic, and name of the topic is L'Hospital's rule. This is a shortcut of finding out the value of the limit using the concept of derivative. When this L'Hospital's rules is applicable, that we will see. Let us take for example limits as x tends to a f of x upon g of x. For sake of convenience, let this limit be equal to L. Now if f of a is equal to g of a is equal to 0. In short, when you take the limits, if the value of the numerator and if the value of denominator both are equal to 0, then this L is in the form of 0 upon 0. And in our earlier video, I already explained the concept that 0 upon 0 is called as indeterminate form. And if it is in this 0 upon 0 form, then only we are going to apply L'Hospital's rule. So L'Hospital's rule can be applied only and only when L is equal to 0 upon 0. Now if I take infinity upon infinity, in certain cases when you talk about the limits of infinity or limits at infinity, you may get value of L as infinity upon infinity. Actually 0 upon 0 and infinity upon infinity are equivalent. So whenever limit are in the form of 0 upon 0 or infinity upon infinity, then only we can apply this L'Hospital's rule. And what do you mean by this rule? So here by L'Hospital's rule, we can write down value of the limit as limits as x tends to 0 f dash of x upon g dash of x. Means in short, we are going to take the derivative of numerator and derivative of denominator separately. Remember, this is not a quotient rule. We are taking the derivative of numerator and derivative of denominator separately. Now if further, if you take limits as x tends to a f dash x upon g dash x, again if it is in the form of 0 upon 0, you can apply this rule further. In short, we can apply L'Hospital's rule for n number of times till we get the answer which is determinate answer. Now we will see in short how this can be applied. You know this formula, limits as x tends to 0 sin x upon x. We know that this answer is 1. If you replace this x by 0, we get sin 0, that is 0, and we get 0 in the denominator as well. Means it is in the form of 0 upon 0 and we can apply L'Hospital's rule. So by L'Hospital's rule, we can take the derivative of numerator and denominator. We know that derivative of sin x is cos x and derivative of x is 1. And now we can take the limits. So cos 0 upon 1 and we get straight away answer as 1. So all these example, whatever we have solved earlier in our earlier part of the lecture or in earlier video, most of the example, if they are in the form of 0 upon 0, can be solved very easily using L'Hospital's rule instead of using standard formulas. Now let us take limits as x tends to 0 a raised to 2x minus 1 upon x. Now here if you want to solve this by using standard formula, we need an adjustment. If it is a raised to 2x, we have to multiply and divide by 2, and then we can apply standard formula, which is limits as x tends to 0 a raised to mx minus 1 upon mx is equal to log a. Now here we can get the answer easily using L'Hospital's rule. We can check that whether it is in the form of 0 upon 0 or not. Denominator is 0. You can check numerator. If you take a raised to 0 is 1 and 1 minus 1 can be taken straight away as 0. So it is in the form of 0 upon 0. We can apply L'Hospital's rule. So by L'Hospital's rule, limits as x tends to 0 as it is, we can take the derivative of a raised to 2x. Derivative of a raised to 2x is a raised to 2x multiplied by log a multiplied by derivative of 2x is 2. Derivative of minus 1 is 0 and derivative of x is 1. And now take the limits. You will observe that if you take the limits, a raised to 0 will be there and which is 1, and therefore we get final answer as 2 log a. So this is one of the best technique to finding the limiting value of the function, but this is limitation of that. This rule can be applied only and only when the function is in the form of, or limiting value is in the form of 0 upon 0 or infinity upon infinity, which is called as indeterminate form. Let us take example number 1. Limits as x tends to 0 1 minus cos of 4x upon 1 minus cos of 5x. Now this problem can be solved by two different ways. One, by using trigonometric adjustment, and then by using standard formula. And if it is in the form of 0 upon 0, we can apply L'Hospital's rule, and comparatively we require less number of steps. First of all, we are going to check orally whether the expression is in the form of 0 upon 0 or not. If you put x equal to 0, there will be cos 0. In numerator, it is 1 minus cos 0, means 1 minus 1 0, and denominator is also 1 minus 1, means it is in the form of 0 upon 0. And now we are going to apply L'Hospital's rule. So by L'Hospital's rule, we get limits as x tends to 0. Derivative of 1 is 0 and derivative of minus cos is plus sine. So it is sine of 4x, and then derivative of 4x is 4. Next, denominator, once again derivative of 1 is 0 and derivative of minus cos is plus sine 5 of x, and then derivative of 5x is 5. Now after this step, again you are having two alternatives. We know the standard formula, that is limits as x tends to 0, sin x upon x is equal to 1. So we can do the adjustment to get the final answer, or if you want, you can use L'Hospital's rule for one more time. Let us use L'Hospital's rule for one more time. Before that, we will check whether it is in the form of 0 upon 0 or not. If we replace x by 0, we are getting sin 0, and sin 0 is 0, and denominator is also sin 0. So again it is in the form of 0 upon 0. So we can use L'Hospital's rule once again. So by L'Hospital's rule, so limits as x tends to 0, derivative of sine is cos of 4x, and 4 we have to take outside, so it becomes 16 cos of 4x, and in denominator we get 25 cos of 5x. Now we know that cos 0 is 1, and that's why we are in a position to take the limits. So here we get 16 into cos 0 upon 25 into cos 0, and therefore we get final answer as 16 upon 25. Let us take example number 2. Again, this example can be solved by doing certain adjustment, and we can use standard formula. But now we will check that whether it is in the form of 0 upon 0 or not, and if it is, we will apply L'Hospital's rule. Replace x by 0, so we get e raised to 0 plus e raised to 0. So 1 plus 1 is 2, and 2 minus 2 is 0. And denominator is 0 square, so ultimately it is also 0. So it is in the form of 0 upon 0, and therefore we are in a position to apply L'Hospital's rule. So by L'Hospital's rule, we can take the derivative of numerator and denominator one by one. Derivative of e raised to x is e raised to x, and derivative of e raised to minus x is minus e raised to minus x. Derivative of minus 2 is 0. And denominator now, derivative of x square is 2x. So let us do the adjustment, use standard formula, or again we can apply L'Hospital's rule. That is up to you. If you replace x by 0, we get e raised to 0 at both the places. So in short, we get 1 minus 1, that is 0, and denominator is 2 into 0, that is 0. And therefore we are in a position to apply L'Hospital's rule once again, and therefore we get limits as x tends to 0. Derivative of e raised to x is e raised to x, and derivative of minus e raised to minus x is now plus e raised to minus x, and derivative of denominator is equal to 2. Now we are in a position to take the limits. So we get e raised to 0 plus e raised to 0 upon 2, and therefore we get final answer of the limit is equal to 1. Example number 3. Limits as x tends to 0, e raised to 2x minus 1 plus x whole square upon x log of 1 plus x. Now here, before applying L'Hospital's rule, I would like to do one adjustment. Why it is so? If you observe denominator, and if you want to apply L'Hospital's rule, we have to take a derivative of denominator using product rule, and if you use product rule, number of steps will go on increasing. and that's why I would like to do the adjustment in this manner. So standard formula is with us, limits as x tends to 0, log of 1 plus x upon x is equal to 1, and therefore this formula I am going to use in this manner. So I am going to separate the term log of 1 plus x multiplied by limits as x tends to 0 e raised to 2x minus 1 plus x whole square upon x. So what is the adjustment? Just I have separated the denominator and I have separated limits into two parts. Standard formula we are having here, and that's why I am going to multiply by x here, so it becomes x square, and divide by x. So value doesn't change. As far as first part is concerned, this is now finite value, that is 1. So can be separated, and now we can see with this adjustment denominator is simple. We are in a position to take the derivative very easily of this denominator, and the complications can be reduced by doing certain adjustment. Concentrate only on this second part. You can check orally. If you see that it is e raised to 0 is 1 and second one is minus 1. Ultimately numerator is 0 and denominator is also 0. So we have to apply L'Hospital's rule only for the second part, because first part value is finite and that is 1 can be separated. So limits as x tends to 0, derivative of e raised to 2x is 2 into e raised to 2x minus derivative of the bracket is 2 into 1 plus x, and derivative of denominator is 2x. If you want, you can go for simplification. We can remove 2 from everywhere. So dividing every term by 2, we get simplified form as e raised to 2x minus 1 plus x upon x. Again we can check. If you replace x by 0, we are getting e raised to 0, that is 1. 1 minus 1, that is 0, and denominator is 0. Means we are in a position once again to apply L'Hospital's rule. So simplifying further, limits as x tends to 0, derivative of e raised to 2x is 2 into e raised to 2x, and derivative of the bracket is derivative of 1 is 0, derivative of x is 1 upon derivative of x is 1. We are in a position to take the limits, so 2 into e raised to 0 minus 1. So ultimately final answer we get as 1. Next example, limits as x tends to y, x raised to y minus y raised to x upon x raised to x minus y raised to y. Now this type of example can be solved only and only by using L'Hospital's rule. We can check it out. X tends to y, so let us replace x by y. We get y raised to y minus y raised to y means 0, and denominator y raised to y minus y raised to y 0. And that's why we are in a position to apply L'Hospital's rule. So by L'Hospital's rule, limits as x tends to y, derivative of x raised to y is y into x raised to y minus 1. Y raised to x means it is in the form of a raised to x. In other words, y is constant term. We know that derivative of a raised to x is a raised to x into log a. So it will be y raised to x multiplied by log y. And now we have to take denominator x raised to x. Now you should know the derivative of x raised to x directly. So derivative of x raised to x is given by x raised to x into bracket 1 plus log x, and derivative of y raised to y is 0 because it's a constant term. Now we can observe there is no 0 in the denominator, means denominator is going to be finite, this ratio is going to be finite, and that's why we are in a position to take the limits. So let us replace this x by y everywhere, and therefore we get this expression in terms of y only. We can use laws of indices and combine these two terms, and therefore we can write down this term as y raised to y minus y raised to y log y upon y raised to y into bracket 1 plus log y. We can take y raised to y common from the numerator. So in bracket we get 1 minus log y, and then denominator 1 plus log y, and therefore final answer is 1 minus log y upon 1 plus log y. Let us take last example of this topic, L'Hospital's rule. This problem can also be solved using adjustment, but I told you many examples can be solved very easily using L'Hospital's rule. First of all, we will check whether it is in 0 upon 0 form or not. If we replace x by 0, we get 8 raised to sine 0, means 8 raised to 0 is 1, and tan 0 is also 0, means 2 raised to 0 is also 1. So in short, we get 0 in the denominator. E raised to 0 is 1, 1 minus 1 is 0, means it is in our standard form. So we are in a position to apply L'Hospital's rule. So let us take the derivative of the term 1 by 1. 8 raised to sine x means it is in the form of a raised to x. So derivative is 8 raised to sine x multiplied by log of 8, and also we have to multiply derivative of sine x, which is cos x, minus derivative of 2 raised to tan x is 2 raised to tan x into log 2 multiplied by sec square of x, and whole upon derivative of e raised to 2x is e raised to 2x upon 2. And now we can observe denominator is a non-zero term, and that's why we are in a position to take the limits. So we can take the limits. So it is 8 raised to 0 multiplied by log of 8 multiplied by cos of 0, we can write down, minus 2 raised to 0 multiplied by log 2 multiplied by sec square of 0 upon 2 into e raised to 0. 8 raised to 0, cos 0, 2 raised to 0, sec square of 0, e raised to 0, all are equal to 1, and therefore we get log 8 minus log 2 whole upon 2. Numerator can be simplified using laws of logarithm. It is in the form of log a minus log b. So we can take 1 by 2 into log of 8 upon 2, and that is log 4. So final answer is 1 by 2 log 4. So this is all about L'Hospital's rule, and using these derivatives we can solve many examples with minimum number of steps. So thanks for joining with us. Thank you very much.